Hello everyone, I am Tianxiang Shen, a PhD student from Hong Kong University, supervised by Dr. Heming Cui. Today, I am going to present SOTER, a secure and high-performance inference system for general neural networks. This work is collaborated with Huawei, Hong Kong Polytechnic University, and Southern University of Science and Technology. Nowadays, giant companies like Google provide well-trained deep learning models to clients. Deep learning models, especially deep neural network, serve numerous mission-critical AI applications in our daily life, such as autonomous driving, home monitoring, virtual assistants, and speech recognition. To obtain accurate models, giant companies must pay substantial training effort to collect private training dataset, tune hyperparameters, and afford huge amount of expensive training resource. Hence, well-trained DNA models are intellectual properties, which are private. To provide high-quality services, these private DNA models are usually deployed on edge-side user devices. Clients run edge-side DNA inference to get real-time results. The basic workflow is shown below. In this workflow, the model provider offloads its private model to the edge. The client constantly sends query input, such as an environment snapshot, to the edge device that runs the offloaded model. By running model inference locally, the edge device returns the final inference result, such as a turn right instruction, back to the client. However, in this workflow, the private model's sensitive parameters are exposed, and since the edge device is untrusted, the inference tasks can be interfered at the untrusted edge. In sum, an edge-side DNA inference requires low latency, high accuracy, with model confidentiality and inference integrity protection. To protect the offloaded model, a pragmatic approach is to use Trusted Execution Environment, or TE, to protect model confidentiality. TEs, such as Intel SGX and ARM Trust Zone, use hardware encryption techniques to form a secure memory space called enclave, which provides both data confidentiality and code integrity guarantees. TEs are widely used to protect edge services. For instance, Samsung uses TrustZone to store sensitive payment information. Trustonic uses TE to build IoT applications with so-called trusted UI. Owing to the prevalence and strong security guarantees, TE-based secure inference systems are emerging, and we will give more details of these systems in next pages. Although edge-side TEs can be trusted, however, edge-side third-party GPUs are untrusted by model providers. This is because CPU TEs does not support GPU acceleration. In addition, although there are some promising TE-integrated trusted GPU research systems, these systems are not publicly available, as they either require extensive hardware modifications or support only hardware simulators. However, GPU is essential for high performance. Numerous edge devices equip GPU to accelerate edge intelligence. For example, Apple's A15 chip equips 4-core GPU. Samsung's new mobile processor includes AMD GPU. We consider an edge-side inference scenario as shown below. We consider the model provider to be honest, which means that the model provider provides the correct model requested by the client. The edge-side TE is trusted as well. However, any components outside the TE are untrusted. We also consider an edge-side attacker that tries to steal the sensitive model parameters and perturb any components outside the TE to modify the inference results. An ideal edge-side inference system should meet the performance and security requirements at the same time. Specifically, the DNA inference running on the edge device should be accelerated with GPU for low latency, and the inference results should retain the same high accuracy as the originally trained model without precision loss. For security, the model parameters plaintext should be hidden. Last, the inference integrity requirement captures the demand that any attacks, such as malicious modifications on inference results, should be detected. Existing TE-based inference systems include TE shielding approach and partition-based approach. The first category of work is the TE shielding approach. Basically, it has 4 steps. First, the model provider attests to the TE-encrypted edge device to confirm the TE device is running the correct code. Second, the server offloads the encrypted model to the edge side TE and then decrypts the model. Third, the edge device constantly takes client input to run inference purely inside the TE, and finally returns the inference result back to the client. Such a simple TE sharding approach has great advantages, including the well-protected model confidentiality and inference integrity, because all the model parameters are hidden in the TE. Even a privileged OS or hypervisor cannot see the parameters and perturb the inference process. Also, it retains high inference accuracy because no modification has to be made on the offloaded model. However, this approach does not incorporate with GPU acceleration and runs inference purely within a CPU TE, incurring extremely high inference latency. This makes this approach unsuitable for mission-critical AI applications which requires low latency interactions. The second category is the partition-based approach. In this approach, a partition strategy from an AI expert is taken as the system input. The partition strategy divides the original model into segments. It places sensitive segments into trusted but slow CPU TE for confidentiality protection, and puts insensitive segments with other plaintext parameters or retrain parameters into an untrusted but fast GPU to accelerate partial inference computation. Apparently, by partitioning partial inference computation to GPU, this approach achieves much lower inference latency than TE sharding approach. However, such an approach incurs either confidentiality loss or accuracy loss. This is because if model parameters with plaintext are partitioned to an untrusted GPU, the accuracy remains unchanged, but partial confidentiality of partitioned model is sacrificed. On the other hand, if model parameters are retrained and then partitioned to the GPU, the confidentiality is protected because no original parameters will be revealed, but the accuracy drops due to the retraining. This is the confidentiality accuracy dilemma. Besides, a partition-based approach potentially has integrity risks because some computations are running outside the TE without protection. We present SOTER, a partition-based inference system that achieves all desired properties for edge-side DNA inference. SOTER accelerates partial heavyweight computation with GPU and retains high accuracy same as the original model. SOTER protects model confidentiality by hiding all parameters plaintext. Meanwhile, SOTER detects any integrity breaches such as malicious modifications on inference results. Comparing to existing edge-side DNA inference systems, SOTER achieves all these desired properties simultaneously. To achieve these goals, SOTER asks two questions. First, how can we utilize untrusted GPU for acceleration without sacrificing confidentiality or accuracy? Second, how can we efficiently detect integrity breaches outside the TE? Before answering these questions, let's have a recap of DNA model architecture. A DNA model can be represented as a sequence of connected layers, with each layer assigned a set of operators as shown in the image classification example below. An operator is either a linear operator or nonlinear operator, where a linear operator is weighted by parameter matrices. During an inference, the model passes an input through layers of operators to finally output the class label. DNA operators widely have an associativity property. First, all linear operators such as convolution and fully connected satisfy this associativity property as they conduct linear transformation on the input data. Also, these linear operators represent a major fraction of computation in inference. Second, some nonlinear operators such as ReLU are scale invariant and thus satisfy this property under specific constraints. For example, when mu is larger than 0, the following equation always holds. Now, to answer the first question, recalling that in existing partition-based systems, if we partition partial model to GPU with plaintext parameters, the confidentiality is sacrificed. If we partition partial model to GPU with retrained parameters, the accuracy of the original model will drop. To bridge this confidentiality accuracy gap, SOTER's key weapon is the general associativity property of common inference operators as shown below. The left part of this equation, which is the original model parameters, are sensitive, which should be kept secret and unobservable by untrusted edge-side attackers. The mu itself is sensitive as well, because knowing the exact value of mu will reveal the parameters of the left part. However, the scaled parameters are insensitive as long as mu is hidden and can be outsourced to GPU for acceleration. Based on this property, SOTER utilizes GPU to accelerate partial heavyweight computation while always keeping GPU operators' parameters secret. The major workflow contains 4 steps. First, SOTER automatically profiles an encrypted model in TE. Then, SOTER morphs a portion of associative operators' parameters with scalas hidden in TE. Next, SOTER partitions these morphed operators to run on a GPU. Last, SOTER executes operators in order, transmits intermediate results between kernels, and finally restores execution results with hidden scalas in TE. As shown in the right example, 2 linear operators which are in red are morphed and partitioned to GPU, while the green ReLU operator is kept within CPU TE. These 3 operators take user input, execute matrix computations with morphed parameters in order, and restore intermediate results with hidden scalas in TE. This process will iterate until the final operator is computed. As a partition-based system inevitably opens access to integrity risks of partition operators outside the TE, it is urgent to detect integrity breaches. To detect integrity breaches, the strawman approach could be a recomputing approach using trusted fingerprints. A trusted fingerprint is produced inside TE before the inference computation. By generating a random input and precomputing the output of a partition operator inside TE, the input and output pair works as a validation code, which we call trusted fingerprints. During the inference, by sending a fingerprint input to the GPU for a proof, we can compare the proof inside the TE with the precomputed fingerprint output. Any mismatch indicates an integrity breach. However, trivially using such an approach is not feasible, because there exists an obliviousness-timelessness dilemma. On the one hand, if we use fixed fingerprints, the adversary can easily observe them and bypass the detection. On the other hand, if we constantly generate new fingerprints as regular user input in CPU TE, fingerprints become oblivious to observe, but the generation process in CPU TE becomes a performance bottleneck, leading to slow detection of integrity breaches. SOTER solves the challenge using the same associativity observation from confidentiality protection. We observe the following variant of linear combination, which can be used to efficiently generate new fingerprints at runtime. Specifically, there are 2 steps. In the first step, SOTER prepares several cornerstone fingerprints in a preprocessing phase before inference. During the inference runtime, SOTER generates random new scalas and uses the above associativity variants to constantly produce new fingerprints in an oblivious manner. In all, by using the same associativity weapon, 3 key modules run in 2 execution phases to collectively provide low latency, high accuracy, model confidentiality, and integrity protection. The Profiler and Inference Manager module speeds out model inference with untrusted GPU while protecting parameters plaintext. Specifically, these 2 modules automatically profile and formulate partition plans and hide partition operators' parameters with hidden blinding coils. The Integrity Monitor module checks partitioned GPU operators' execution results to detect any possible integrity breaches. These 3 modules constitute the whole architecture of SOTER. We implemented SOTER on PyTorch and Graphene SGX, but SOTER is extensible to any imperative deep learning frameworks and TE codebase. We adopted a 2-phase design for offline preprocessing and online inference. We designed a morph then restore protocol for cooperative executions between kernels. We designed a periodical updating mechanism to prevent chosen plaintext attacks. We also designed an on-demand operator prefetching mechanism to reduce TE memory footprints. For the baselines, we evaluated ML Capsular, EdgeSTN, and Enclave. ML Capsular is a TE shielding approach. EdgeSTN and Enclave are state-of-the-art partition-based approaches. Note that the above blow optimization is also incorporated in the 3 baselines. For the evaluation, we run all experiments in our cluster. We use a server with real SGX hardware support. We used a GPU farm with NVIDIA GPUs. Each GPU had 11 GB physical memory. We evaluated 6 prevalent DNNs covering both computer vision and natural language processing tasks. We asked the following questions. First, how is SOTER's end-to-end performance compared to baselines? Second, how is SOTER's confidentiality protection compared to baselines? Third, are SOTER's trusted fingerprint oblivious to the adversary outside the TEE? Last, how sensitive is SOTER's performance to different partition ratio? We will report the top 3 questions in next slides. For the end-to-end performance, Figure 1 shows the inference latency, which is normalized to insecure GPU inference compared to 3 baselines running 6 prevalent DNN models. SOTER achieved 1 times to 4 times lower inference latency than TE Sheridan baseline ML capsule, as SOTER securely utilizes GPU to accelerate partial heavyweight inference computations, including the convolution and fully connected operators. And even SOTER pays additional effort to enforce integrity protection. SOTER incurred only moderate overhead than partition-based baseline HSDNN. Even if SOTER completely hides partition operators' plaintext, an adversary may still conduct model stealing attacks to train a substitute model. Hence, we run model stealing attacks on all baselines and use the accuracy and BLU score as a metric to evaluate the confidentiality. Figure 2 shows the accuracy and BLU score of the trained substitute model. Note that a higher accuracy or BLU score of a substitute model means more confidentiality loss. SOTER achieved stronger confidentiality protection than HSDNN, which implies that morphing operators by scaling its parameters hides significant model information compared to HSDNN, which directly partitions model parameters plaintext to untrusted GPU. Meanwhile, SOTER achieved the same strong confidentiality protection as Enclave, while Enclave sacrifices inference accuracy, because Enclave retrains partial model parameters to hide the original operator's parameters on the untrusted GPU. To validate the integrity protection, we compare SOTER's oblivious fingerprint with the Strawman fixed fingerprint approach. Figure 3 shows that SOTER's fingerprints are oblivious to the adversary, because the L2 distance distribution of fingerprints shares the same form of normal distribution as client's normal query input, while the L2 distance distribution of fixed fingerprints does not share the form of normal distribution. To conclude, in this paper, we present SOTER, the first work that achieves model confidentiality, low latency, and high accuracy with integrity protection for general neural network inference. SOTER achieves comparable strong confidentiality as TE shielding approach, comparable low latency as partition-based approach, high accuracy same as insecure GPU inference, and overwhelming high probability of obliviously detecting integrity breaches. These features encourage giant companies to develop powerful models and deploy them on third-party edge devices. Meanwhile, SOTER can also help with protecting models on untrusted cloud servers. SOTER's future work is broad. SOTER can integrate with emerging black box defenses to further strengthen its privacy guarantees. Also, SOTER can be extended to multiple GPUs and TEs for distributed model inference. SOTER's artifact is available on our group's website. Thank you. That's all for my presentation, and I'm happy to take questions now.